I'm from TU Munich, from the chair of applied mechanics, and I have to admit I have ignored the swing lag for a long time. And it seemed to me that literature is backing me up on that. So it seems there are some good ideas how we swing our lag, and a lot of simple models ignore the swing lag, and they match human walking dynamics pretty well. So what we see here is experimental data, the horizontal motion of the center of mass and the ground reaction force, and this is the same thing from the inverted pendulum model. Pretty good fix. And so my German punctuality gene would tell me now, isn't that great? End of story, we are back on schedule. But a couple of our roboticists started to look at our robot, and we were looking for virtual pivot point. And I published the results 2 weeks ago. I don't want to go into that. But when I looked at the ground reaction forces that came out of the planning of this robot, and also the ground reaction forces that we saw when the robot was actually walking, I saw that they were flipped. So they were pointing in the wrong direction. And I was thinking, like, why would that be? What if there are systems where the swing lag actually has an influence on the general dynamics of the of walking? And so I looked at a swing mass model, at the inverted pendulum model, and in planning we use a 3-mass model. So I think it was called potato model before. We have a mass distribution, 2 masses at the feet, and a reduced mass at the trunk. And in the planning of Lola, essentially there's just a prescribed trajectory that the leg is following. And I was thinking, like, yeah, but Lola's gait is not quite human gait. So what if I just try to mimic human gait as best as I could? And so I said, okay, like, let's just assume there is an acceleration here. And this acceleration has to come from somewhere. I wanted to keep the model simple, so I didn't introduce any trunk or anything. So I said, like, there is a force here. It has 2 components. One force component acts along the leg, so there are 2 additional degrees of freedom here, the leg length of the swing leg and the interleg angle. And the projected force actually also projects on theta, the vaulting angle of the model. And a second component is a torque. There is nothing to generate the torque other than pushing against the ground. And I put that into equations of motion. I parameterized the time for swing and formulated 2 parametric accelerations for the swing leg. And then I asked an optimizer to actually find me a solution where the swing time matches the vaulting time, where the leg is fully extended at the end of swing, and we have a matching symmetric angle of attack. And the optimizer came up with variables that were quite close to human walking, so we have an average walking speed of 1.3 meters per second, which is close to normal walking. We have a swing time of about 470 milliseconds, which is a little bit on the long side, but not too much. And the acceleration, the maximum acceleration that I need in horizontal direction is pretty high, 35 meters per second squared. And so how does that look? We have 3 models here. The conventional inverted pendulum model, a little bit faster in vaulting, a model that just passively pulls the leg along, and then the model that actively accelerates the swing leg. And you see the vaulting dynamics are not that much impacted, but what we see is what we observed also in Lola. The ground reaction forces actually flip. And this is the interesting thing. So I tried out different mass distributions from putting less than 1% of the total body mass into the foot, up to 11%. This is what we found is a pretty good representation of the mass distribution. And you see the more mass obviously you put into the foot, the more this flip of the horizontal ground reaction forces actually happens. And so, in summary, what I want to show here is that leg swing in general requires high accelerations, which could have a substantial impact on ground reaction forces. This can be observed in robots that power leg swing from the hip joint, and the good match of models that we observe and which ignore the swing leg suggest that there is indeed, as we knew before from the beginning, something going on that decouples the swing leg dynamics from the rest of the body. Thank you very much.
Just for your swing trajectory, were you like trying to reproduce the swing trajectory that you tend to execute on the robot?
No. So essentially, I just thought, okay, what acceleration profile would get me the leg where I want it to be? So I said, like, horizontally, what I need is a positive acceleration initially and then a negative acceleration. So I get a good ground speed matching at the end.
Well, I guess maybe like the graphic doesn't give enough details on what the swing is actually doing. It feels like from the graphic, it feels like the foot is coming to a stop at the end.
Yeah, it pretty much does.
And
so this is the acceleration that I'm putting.
I guess like my point is there. It seems like you could probably like come up with different shapes of trajectories that have like large variations in acceleration at takeoff and touchdown.
Yeah.
That would lead probably like to different shaping on your results.
Yeah.
And so I was wondering if you like
So
with that.
I would argue that this might be like you could have higher peak accelerations. So I would say this is a pretty smooth acceleration trajectory, and it still has this flip in vibration.
Couldn't you get even a sign change if you raise the center of mass on the leg? So right now you have the passive swinging is too slow, and you have to apply torque to speed it up.
Yes.
But if you move the center of mass, only a quarter of the way down from the top, not that that's the right place, but then you have to apply torque in the opposite direction.
Possibly. Haven't tested.
Right? You understand what I'm saying?
Yeah, I understand what you're saying. So I move the mass up,
Yes.
and then I get I get a faster speed. Yeah, and this could be what we essentially like. Where this model comes from, this is what we put into our planner in the robot, and actually, like, Lola has fairly heavy legs, so any mass distribution is not so much different from humans. And still, in the robot experiments, we see this flip in ground reaction forces. And I was asking, like, where might that come from? Yeah.
So this one, when you're going into swing, the leg goes straight up, lifts up, and then goes forward.
Yeah. So,
but in human walking, my understanding is that mostly it's the toe off pushes the leg into the swing leg at speed. Is that correct?
So yeah, this is what
torquing it once it's in the air.
McMahon, I don't get it together. Like what they said initially about ballistic walking. So you give it a push, and then it flies through the air. And like that would be one reason why the swing leg dynamics don't show up in the ground reaction forces. So I'm not saying this is what it is. Yeah.
So to me it looks like the swing leg dynamics are showing up because you are not countering them with the upper body. And the same might be happening exactly with Lola because you're not actively controlling the upper body.
We are actually actively controlling the upper body, but we try to keep the angular momentum of the upper body zero. And this is why...
Just the upper body angular momentum, or the whole system?
No, not the whole system. So
you're trying basically to keep the upper body still?
Yes. And
so
this
you're
is
not counterbalancing the...
Yeah. And this is an interesting question, and I would like to see, and I think like Emmy and Peter already did that, to look essentially how much an upper body could counter the this effect of the
Using your model, would you say it would be a good performance metric for like just designing legs and forward swinging or so? Do you think your model would capture that?
I'm not sure. To design what?
Yeah, if you were designing a leg that was just layered down here to the ankle, do you think
Yeah.
this model could compared to the design as well?
Yeah, so I think there are a couple of factors that we see in some robots, like lightweight legs or extended swing legs, that extended swing times that actually reduce the problem that we are seeing. But in normal human walking, our swing time is fairly short, so we see these high accelerations, and the more mass you have to accelerate. And if you do that during swing, then you see an effect like that. But yeah, you can. There are a lot of design options that you can choose. Okay. Thank you.